Look at Venus through a standard optical telescope, and this is what you see: a thick, unbroken layer of clouds hiding the surface. It is overwhelmingly, stubbornly featureless. In 2010, researchers aimed an experimental polarimeter at Venus, measuring how light waves were oriented instead of standard brightness. It revealed massive concentric rings wrapping the dayside. Stretching thousands of kilometers, these patterns were recorded for exactly 36 minutes before the instrument was permanently dismantled. We know this atmosphere is hostile. It is a crushing envelope of carbon dioxide topped by thick layers of sulfuric acid. Creating an organized, planet-wide geometric pattern in that kind of chaos requires an immense amount of energy. This leaves us with a stark choice. Either a colossal, unidentified physical mechanism is operating right next door in our solar system, or a very expensive piece of equipment simply malfunctioned. Down on the rocky surface, Venus is nearly stagnant. The planet barely moves, taking 243 Earth days to complete a single rotation on its axis. But the atmosphere above it is tearing across the sky. The cloud tops whip completely around the planet every 4 days, moving 60 times faster than the ground below them. Astronomers have tracked this phenomenon, known as superrotation, for over half a century. We have sent probes to map the winds and orbiters to measure temperature, yet the exact physics continue to elude us. The 2010 data maps these immense rings directly onto the path of the atmosphere's superrotation. If the physics match, these patterns represent the visible footprint of the exact mechanism driving those extreme winds. Discovering a coordinated, planet-spanning structure hidden inside the cloud layer gives researchers a physical target. If we can explain what created these rings, we might finally map the energy flow of the entire Venusian climate. The data came from the Extreme Polarimeter, or ExPo, mounted high in the Canary Islands on the William Herschel Telescope. ExPo was never built to look at Venus. Engineers designed it to hunt for exoplanets. By aggressively filtering out the overwhelming glare of a host star, it was meant to detect the incredibly faint light reflecting off distant, orbiting worlds. It achieves this using polarimetry. Normal cameras just measure how bright light is. Polarimeters measure light's geometry. When photons scatter off gases, their waves orient in specific directions. In Venus's upper atmosphere, Rayleigh scattering occurs. When sunlight hits carbon dioxide molecules above the clouds, it scatters and becomes highly polarized. Because ExPo strips away the blinding, unpolarized glare of the clouds, it isolates the light bouncing off the gas itself. It acts like a high-contrast dye, highlighting structural mechanics in the atmosphere that ordinary lenses simply cannot register. When researchers first saw concentric rings spanning the entire Venusian disk in the ExPo readouts, they assumed the instrument had glitched. They spent years attempting to debunk their own finding. The team cross-referenced the observation phase angles and double-checked the different filter widths, looking for any optical or mechanical error that could have generated a false positive. But they couldn't just take another picture. By the time they realized what they had found in the data, the experimental ExPo instrument had already been taken apart. The 36 minutes of data were all they had. Unable to verify the rings with a telescope, the team turned to physics. They fed atmospheric data into the Venus mesoscale model to see if the environment could naturally produce this kind of geometry. The models pointed to atmospheric gravity waves. These are not ripples in space-time, but massive density waves, areas where the gas itself compresses and expands as energy propagates through the fluid atmosphere. This graph illustrates the breakthrough. The flat line shows that total brightness remains constant, but the wave shows that a variation of just 5 to 10% in the carbon dioxide density perfectly reproduces the polarized rings recorded by ExPo without leaving a trace in standard visible light. The data alignment is precise. These rings represent the optical signature of colossal density waves propagating through the upper layers of Venus. To understand where these waves come from, we have to look at the subsolar point, the exact location on Venus where the sun is directly overhead, pounding the atmosphere with intense, unyielding radiation. The researchers hypothesized that this concentrated thermal shock acts like a stone dropped in a pond, triggering massive planet-wide ripples that expand outward from the equator toward the poles. This animated cross-section shows how that energy moves. As the density waves travel, they transport momentum upward from the lower cloud decks. depositing kinetic energy into the upper thermosphere. That vertical transfer of momentum provides exactly the kind of sustained, powerful mechanical push required to keep the entire upper atmosphere spinning every 4 days. The team is explicit about the limits of their work. A single, unrepeatable observation from an experimental rig does not settle the physics of an entire planet. They publish their findings to put the astronomical community on notice. The data is a blueprint, showing other observatories exactly what to look for when they aim modern polarimeters at Venus. The frontier of space exploration can exist in the archives, waiting for new analytical tools to uncover what was sitting on a hard drive for a decade. Those 36 minutes proved that we are still blind to the mechanics of our closest planetary neighbor. Until we launch dedicated polarimetric missions to look again, the engine driving Venus remains hidden in the clouds.